Today's professional test pilot differs from his earlier counterpart only in the scientific knowledge and technological hardware he has accumulated. The pioneering spirit and dedication to the scientific method of exploration, this he shares with his predecessors. The era of the modern-day test pilot began at 10:35 a.m., December 17, 1903, when Orville Wright became the first American to experience heavier-than-air, powered, controllable flight. The Wright brothers managed the complete cycle of aircraft design through flight test. They built their own wind tunnels and plotted their own test procedures. They also had to design and build the first propeller and lightweight engine to power their glider. Wilbur Wright expressed the credo of the test pilot by saying, "If you are looking for perfect safety, you do well to sit on a fence and watch the birds. But if you really wish to learn, you must mount a machine and become acquainted with its tricks by actual trial." The Wright brothers had, in effect, become the first formal test pilots. Casey Jones was a test pilot for Glenn Curtiss. He was also an exhibition pilot and barnstormer. This type of undisciplined flying bored the more serious aeronautical engineers. As George Van Doors wrote, they could only discuss flying in terms of muscular exercises and sensations. Jimmy Doolittle was the first test pilot to receive a doctorate in aeronautical engineering. Thus began the trend toward academic requirements for future test pilots. Flying a Curtiss R3C2 biplane racer, Doolittle won the 1925 Schneider Air Race with a world record speed of 245 miles an hour. After mastering the deadly GB Racer, Doolittle declared that racing had outlived its usefulness. He believed that the benefits gained from racing would not be worth the personal risks. Doolittle also pioneered instrument flying. Collaborating with Elmer Sperry Jr., Doolittle made the first blind flight using only instruments on September 24, 1929. His consolidated NY-2 trainer was the first aircraft equipped with an artificial horizon, gyro compass, and precision altimeter. This flight represented a monumental advance in aviation safety. Following in the tradition of the Wright brothers, Charles Lindbergh played a crucial role in the design of the Spirit of St. Louis. He personally flew the test flights and recommended modifications that would enable him to make the transatlantic flight. Air Force historian Richard Hallion said, "It was with the full confidence of a test pilot who thoroughly understood the capabilities of his airplane and equipment and himself, and certainly not the reckless act of a flying fool." During World War II, Lindbergh evaluated a variety of aircraft, including the North American P-51 Mustang and the Boeing B-29 Flying Fortress. In 1944, Lindbergh flew 50 combat missions in the South Pacific as a civilian test pilot and downed a Japanese Zero while flying a Lockheed P-38. Many of the growing number of test pilots saw service in the Second World War. They were employed at the aircraft production plants and at the delivery depots near the front lines to ensure operational suitability. The war also became the training ground for many a future test pilot, the most prominent being Charles E. Chuck Yeager. Yeager and many of his contemporaries were confronted with one of the great challenges in aviation history, exploring flight beyond the sound barrier. On the morning of October 14, 1947, Chuck Yeager in the XS-1 was the first human to successfully fly an aircraft beyond the speed of sound. Supersonic flight gave birth to a new era in aircraft development and a new set of unknowns for the test pilot. With the discovery of new propulsion systems and aerodynamic principles and the radical change in aircraft design, the test pilot became more important in the development of the flying machine. Bill Bedford, first test pilot of the Hawker P-1127, predecessor to the Harrier.
I was always inspired by the pioneers like the Wright brothers and Sir Thomas Sopwith and Lindbergh and so many others that I had admired. And this, of course, reflected, I suppose, in my own experience in operational flying of aeroplanes and being called upon to do things like air tests after inspection. And I felt I wanted to go deeper into things than just use the aeroplane operationally. I wanted to start with it from the sparkle in the designer's eye, be integrated with the program, and then develop it with the flight development team into operational service. The forerunner of the Harrier, the P1127, started as a sparkle in the designer's eye in 1957 in parallel with Bristol Siddeley Engine Company and our own company, Hawker Aircraft Limited, with some brilliant young designers who came out with some formulative sketches. I think it was exciting from the point of view of realizing that we were involved with a new concept, a new aeroplane, a new engine, and an enormous number of unknowns. The first transitions were technically, I suppose, and politically a very important step forward that proved the fundamental concept. So they were an exciting period for us in our career. I think where we really saw the potential of the aeroplane was when we started doing short takeoffs, in which the aeroplane could carry about 4 or 5 times more load when you have the wing and the engine lifting at the same time rather than doing a vertical takeoff. And that really put the machine in the right perspective.
The X-15 program clearly illustrated the complexity of the modern-day flight test regimes, and it brought to the forefront a new breed of test pilot who combined aeronautical engineering experience with consummate flying skills. Scott Crossfield, aviator and aeronautical engineer.
My role models were the Wright brothers. They completed the whole circle. They got involved in the concept, the criteria, the requirements, the performance spec, the detailed spec, the manufacturing and the quality control, and the managing of a new and innovative works. And they did it in a very credible way that we could emulate very well today. In 1898, they established a program to fly in 1903. And they stuck to that plan, except to when they had to deviate and build their own engine. They built wind tunnels, and they did fly in 1903. Actually, they were the first systems integration engineers and gave us the example that we hold as the way to do business today. Well, on the X-15, I was very fortunate in being able to complete that whole circle. I was involved in that airplane from concept all the way through to the demonstration of a new and innovative works. And I think that's probably one of the best things that could happen to an engineer and a designer like me.
The calculated risk accepted by the test pilot in answering the ultimate question, will it fly, is perhaps the most intriguing and seductive part of the job. And as Crossfield relates, the risk can start before the aircraft leaves the ground.
When we installed the large engine on the X-15, and for reasons of our flight test plan, we were going to demonstrate that that engine could be started, it could be throttled from 50 to 100% as designed on the first flight. The way we were flying, I was limited to the speeds that I could allow the airplane to get, so it took a very precise engine on, off, and thrust program to stay within that flight plan. To make sure that all the systems would respond to this plan, we made the last test of the engine in the airplane on the ground. And it's kind of humorous because the pilot gets in the airplane to run the engine and everybody else gets in the blockhouse. That's called developing the confidence of the aviator. And during that run, we had a propulsion system failure that was born of some things unique to the ground run that caused the airplane to blow up. And about 1,000 gallons of liquid oxygen and 1,200 gallons of anhydrous ammonia and 800 pounds of 98% hydrogen peroxide got together and did their chemical thing, and it was a pretty violent activity for a moment or two. It was like being in the sun. It was such a fire outside that it was very brilliant orange. And the forepart of the airplane, which was all that was left, was blown about 30 feet forward, and I was in it. And of course, I was pretty safe because I was in a structure that was designed to resist very high temperatures of re-entry flight.
And rising like the phoenix from the flames, Scott Crossfield made the first flight in another X-15 with the XLR-99 engine, only 5 months after his near-fatal experience with the engine's ground test. He took the craft to 80,000 feet and a new speed record approaching Mach 3. Bob Smythe, former chief test pilot at Grumman, was the first to fly the F-14 Tomcat in 1970.
The risk of being a professional test pilot is that we live in a two-dimensional world. The test pilot explores the third dimension. So there's got to be a little bit of hazard to that. If he's lucky, he gets there before other people do, and that's part of the interest of the business. But it's not an overpowering thing. If it were, you just wouldn't do it. It's a good way to make your living, and it's an interesting way, and every day is different, and it's fantastic.
Smythe was in the back seat on the second flight of the #1 F-14. William Miller was at the controls. In this recorded sequence, we see and hear the final dramatic moments of that flight, from which both pilots survived.
Well, the geometry on this stick is miserable.
Wonder who designed that?
I don't know. Yeah, okay, there goes a little there. Whoops. Flight control, I've lost the flight control system.
Let her go.
Oh, all right, just a second. No, I can't hold it.
All right, eject it. The airplane just dived right into the ground. And Bill initiated the ejection. We had these wonderful Martin Baker ejection seats. 0.4 of a second after the Bill's seat, the second seat, left, I went straight up. Good rocket seat took me right straight up because the airplane was more or less upright when I went out. And the parachute opened and everything looked great. I looked down and there was a bloody airplane right below me. 10,000 pounds of fuel were burning furiously. It was right below me. And you won't believe this, but you're kind of insulated or isolated or something at that time, and it's as though you're kind of standing off in a distance looking. You say, son of a gun, I'm going to land in that fire. And that's just about as emotional as you get over it. Luckily, I didn't try to steer the chute. I didn't have the presence of mind to do that, because when you steer the chute, all you do is you kill lift and you sidestep it, and that might have been enough to slip me into the fire. We had about 20 knots of wind blowing that day, right down the runway. And while I was sitting over this fire, oscillating, presumably descending a little bit, I got over to the kind of leeward edge of the fire and got lifted by the heat of the fire, and I could feel myself going up. And in subsequent photographs, this was excellent for ejection seat training movies. We had cameras all over the place because it was the real, essentially, first flight of the airplane. Showed after the smoke cleared, I was really higher than I was before the smoke enveloped the parachute the first time in the photographs. And it just deposited me about 100 yards downstream of the burning airplane, downwind of it. And I chute caught the top of these trees, and I plumped down on my rear end in the leaves, and everything was happy.
Neil Anderson was a test pilot on the F-16 program for 10 years.
The issue of risk is a question that all of us deal with consistently. Are we risking our lives when we walk out the door to step in our car in the morning to go to work? Certainly there is some risk involved. Are we risking our lives every time we strap on an airplane to go out for a test mission? Certainly there's some risk involved. The two are somewhat similar, but on the other hand, when you step into an airplane to do a test mission, much of the success of that mission and much of the risk involved depends upon your ability rather than the ability of somebody else. Every airplane has its growing pains. The F-16 is no exception. One of my early experiences on the airplane involved a landing with the wheels retracted. A lot of things go through your mind at a time like that when you're making that kind of a decision. It was my belief that with the engine shut down and the engine not turning, the risk from this sort of problem would be minimized. So I made up my mind to land the airplane in the grass beside the runway with the engine shut down in flight and not turning in flight so that I wouldn't have an ingestion problem that caused an explosion. But I did think we'd be able to recover some of the parts from the airplane. We only had 2 prototype airplanes at the time, and I wanted to save as much of it as I could. One of the best examples I can think of test pilot reaction to an unusual circumstance is a brief review of my colleague Phil Ostreicher's amazing talent in recovering the first YF-16 on its taxi test. His mission was to accelerate the airplane to above 100 knots on a high-speed taxi and apply a roll input to check roll damping. As he got the airplane above 100 knots, he pulled the throttle back, perhaps didn't pull it back far enough. The airplane continued to accelerate. The airplane was flying. When Phil put in the roll input, the airplane started a pilot-induced oscillation. He had an oscillation where the wingtips were hitting the runway, the tail was hitting the runway. He elected to abandon the roll and apply pitch, fly the airplane out of the problem because he recognized the problem was more than he could cope with quickly, that quickly. That's the significant part of a test pilot's expertise. Not only conducting the test as he needs to conduct it, but being able to recognize and compensate for a highly undesirable situation.
Today, the test pilot is a thoroughly integrated member of the design and developmental team. With the engineers, he understands the theory behind the design objectives and the safe operational limits of every component of the airframe, control system, propulsion system, avionics package, and the function they serve in the performance of the aircraft. He is involved in a highly discrete incremental testing procedure that will start with simulation trials on the ground where possible of all test regimes before ultimately taking the craft aloft. Here at Grumman's Calverton, Long Island plant, the F-14 structural test vehicle, currently being used to test performance enhancement concepts for the Super Tomcat program, will be flown on a test mission by Chief Test Pilot Kurt Schrader.
The intent of this program is to increase the maneuvering envelope over that of which the airplane was originally designed. We accomplish this by using an airplane that's very heavily instrumented so that the structural loads throughout the airplane are measured and transmitted real-time to the automated telemetry station. There, the engineers are monitoring these loads and determining whether they're acceptable or not.
On the scheduled day of the mission, the test pilot reports to operations and checks the weather conditions over the test range. The time of departure is confirmed and noted on the flight board. The flight crews then proceed to the pre-flight briefing. Neil Jansen, the test conductor, begins the briefing.
Pre-flight maintenance first, and then we'll do the technical brief. Bobby?
Okay, aircraft maintenance status is as follows. All discrepancies from last flight have been resolved. There are no open gripes against the airplane. Pre-flight has also been complied with. All instrumentation parameters have been checked and are up, and the instrumentation system pre-flight has also been complied with.
We'll start with the ICS and UHF checks. We'll then do the IRIG sync on the airplane. We'll do the alpha and beta cals, and then we'll get an arcal on tape. We want to see the tape run light, so that'll take about 10 seconds.
Okay.
Okay, we'll set up 0.82 Mach, 35,000 feet.
After the test conductor covers the maneuvers described on the test card, Schrader addresses questions to the individuals who are responsible for specific areas related to the performance of the mission.
Before we get into a detailed description of the maneuvers that we're going to accomplish today, we have a safety input for the flight?
I checked with Tracker. There are no range restrictions. You have clear range from surface to 50,000 feet for the whole day.
Okay, as we're going to be in an area here that high altitude, high angle of attack, low airspeeds, there's always a possibility of an engine stall. A check from the power plant standpoint, how are we going to deal with that?
Okay, the big worry is temperature in this situation. We'll be watching that on the brush tables and on the screen. If there's no problem, we can just come back to idle and go on with the test point. If the engine looks like it might go into hang stall, we'll ask you to take a cut. We'll give you that call real time.
Okay, Paul, from a flying quality standpoint, when we're going to obviously transgress into a high alpha regime here, how do you intend to deal? What are you watching there on the tables?
Well, what I'll be watching on the table will be angle of attack and yaw rate. If I see that the airplane gets away from me and I haven't noticed the proper recovery controls going in, I'll give you the direction of departure and I'll give you a call on the proper recovery controls to be putting in, and then we'll monitor from there.
Okay, Tom, from the standpoint of the Navy input on this, being a structural program and you're the actual witness, or do you have any inputs as far as what you need in the station?
I'm going to be watching the flight to make sure that the test points are done on the proper points in the sky with the right control inputs and the proper test techniques. I'm also going to be monitoring the loads that we're going to see in the flight to make sure they're what we expect within the proper limits of the airplane and that type of thing.
Also, this being the end point for the flight, from a structural standpoint, Dennis, what are your concerns as far as the limits on the airplane?
Critical area would be the air fuselage after station 580, and the worst case would be the maneuver with the flaps extended. We expect to get about 80 to 90% limit.
Okay, Joe and Stewie, the chase procedures are as normally briefed. The only thing of particular attention on this flight is if we have a problem with the airplane.
With the briefing completed, the flight crews don their G suits, pick up their flight gear, and head for the flight line. At this time, the number 3 aircraft is towed to the ramp, and there joined by the chase plane for fueling and pre-flight check for both aircraft. The flight crew arrives on the ramp. Schrader and his radar intercept officer perform the required walk-around inspection of the aircraft. In the cockpit, instruments are checked and controls tested. The aircraft are cleared for taxi to the runway. Here in ATS, the Automatic Telemetry System facility, the test conductor, Neil Jansen, supervises the preparation for the test mission. This automatic telemetry system will record the test data in real time, enabling the engineers to analyze the resulting stresses on the aircraft as the maneuver is being performed and report it to the pilot immediately with an evaluation of the results. On the basis of this information and the established safety limits, the decision to perform the next level stress maneuver will be made. 5 miles away at Terry Hill, the telemetry tracking station is readied to track the number 3 aircraft as it performs the test card maneuvers, receiving data from the aircraft and transmitting it to the recording station at the Calverton plant. The Grumman traffic station is preparing to monitor the test and make certain all airspace in the test range is clear. The safety officer will monitor the flight from his office, where he monitors all voice transmissions from the aircraft and the ground stations for any sign of problems. Back on the field, the crew has performed the final pre-flight engine run-up, and the final exterior inspection is made. The tower clears number 3 for takeoff.
Cleared takeoff.
Arriving at the test range, number 3 performs a series of standard check maneuvers to ensure that the aircraft and instrumentation are functioning properly. The first is a left level roll. At the telemetry station, this maneuver is displayed in real time on the silicone graphics screen and recorded on videotape. The next check maneuver is a right level roll. After a left pedal side slip and a right pedal side slip, the final check maneuver is a left wind-up turn to 3 Gs. The initial test maneuvers consist of a series of wind-up turns, each with incrementally progressive G loading, initially performed with an aerodynamic surface called the glove vane, first extended, and then repeated with the glove vane retracted. The wind-up turn is a standard flight test maneuver where the pilot manages the aircraft's energy state to maintain Mach number or airspeed while increasing the G and angle of attack to the target level of the test point. The objective here is to measure the structural loads at a given flight condition. Schrader performed 16 wind-up turns to complete the first portion of the test card. The PHAA, or Positive High Angle of Attack maneuver, is essentially a rapid symmetrical pull-up. This point combines high structural loads with significant levels of inlet distortion, which are required to evaluate a new engine inlet seal design. The maneuver provides a rapid change in both flight path direction and aircraft energy state, which are important characteristics in the tactical air combat maneuvering environment. The final maneuvers are a series of 5G brake turns, starting at 350 knots indicated airspeed, and increasing in 3 increments to 450 knots. Each brake turn at the indicated airspeed performed twice. First with the glove vanes extended, and then with the glove vanes retracted. When all the tests on the card are completed, the aircraft returned to base. As we have seen, the test pilot's day-to-day role is dramatically different from that of the pioneers of flight testing. Today's high-performance military fighter aircraft is a sophisticated integrated package of aerodynamic propulsion and weapon systems, sensors, actuators, and computer software. Each flight test is preceded by hours of simulation to predict the outcome. And then the actual test flight is monitored in real time with automatic telemetry by dozens of engineers. As one test pilot described today's flight test environment, it's like having a room full of engineers with you in the cockpit. But the test pilot's objective, to ensure that the airplane performs to its design specifications, remains the same. Heinz Frick, Chief Test Pilot at British Aerospace, Dunsfold, currently assigned to the Harrier program.
Well, basically, the amount of flight testing that we do on systems development is getting ever greater. Clearly, there's software development to be done, but a lot of that can now actually be achieved in simulators. However, the final proof of the pudding still is you have to hang the weapon on the airplane, you have to prove that the weapon ultimately falls in the right place. And of course, if engineers were all perfect, there wouldn't be any need for test pilots. However, even when we've gone to the flight envelope, we tend to go beyond it, obviously, in order to make the aircraft safe for the service pilot, because we give him a set of limitations that he has to perform to. Every now and then he will go outside those limitations. We must make sure that that boundary is still safe. And so the flight test work that we undertake, as I said, is not just software development, which plays a never-increasing part, as I've just said, but the clearance of the overall aircraft in terms of handling, performance, weapon aiming, weapon delivery, emergency procedures, everything that is associated with a flight of something like a Harrier here is what we test.
Soviet test pilot Anatoly Kvatsur's MiG-29 flight display at the 1988 Farnborough Air Show graphically illustrated how a methodical, step-by-step program of exploring a new aircraft's capabilities can produce dramatic results. The hammerhead stall and tail slide, demonstrated here, was repeated flawlessly day after day at relatively low altitudes. This maneuver is rarely attempted in a jet aircraft and speaks well for both an aircraft's integrity and the pilot's skill. It also represents the culmination of meticulous testing that confirmed the airframe and engine would tolerate such a maneuver and continue to function reliably. Anatoly Kvatsur.
And vertical maneuver is not very difficult for our pilots on our aircraft. And hope that all pilots will to do that maneuver.
Well, I have talked with some people who have said it's a very difficult maneuver to do at the low altitude that you do it at.
Но я много людей встречал, которые говорят, что это довольно сложно на такой небольшой высоте делать этот маневр, как вы делаете.
Силовая установка работала нормально.
Я повторяю, значит, для нашего самолета это несложно.
It is not difficult to do for our airplane.
И мы делаем этот маневр с очень большим запасом. Запасом приблизительно в 3 раза по высоте.
And we are doing this maneuver with 3 times altitude more than it can do this. We are doing it at the greatest height.
At what altitude would you normally do it?
А на каком высоте вы вообще можете сделать этот маневр?
Значит, минимальная потеря высоты, которую мы достигали, около 200 метров на вывод из этого режима.
The minimum decreasing of the height is about 200 meters from the top of the maneuver.
So you can do it at quite a low altitude and feel comfortable that the engines will continue to respond.
И вы можете это делать на меньшей высоте, и у вас все будет нормально. Yes, yes, we can do it.
We have no problem with our engines.
No problem.
Yes.
It is main.
Yes.
It's the main question. We have no problems with engines.
There comes a point, though, where nationalities fade, and the Soviet becomes one with his test pilot brethren all over the world. That is when he is alone with his aircraft, when he takes it into the air and puts it through a rigorous pre-planned program of precise maneuvers to determine exactly what it will do. Through a careful incremental build-up process, he flies the aircraft through increasingly aggressive climbs, dives, high G turns, stalls, and endless system checks, all precisely flown tests that will yield the data needed to characterize the new vehicle. Flying skill are both at work here, exploring limits while exercising caution, memorizing split-second nuances that might later explain something the data system missed. All the pilot's skill, training, and judgment are focused on unlocking secrets the aircraft might have and discovering them under controlled test conditions, not after it is in service. And when he lands after each flight, the test pilot knows a little better whether his new aircraft will meet its design goal and whether it will be an airshow crowd pleaser as well. While the glamour associated with a test pilot's work resides in the high-performance military fighter aircraft, the skills of the test pilot are employed in the development of all aircraft. The test pilot's experience and ability to do the job of rigorous flight testing to ensure safety, operational performance, and marketability of the production aircraft and its derivatives are critical. Elmer Walls, senior test pilot with Westland Helicopters.
Testing is obviously a glamorous job as far as everybody else is concerned. It's like it can have its boredom, it can have a lot of excitement. The helicopter in relation to the fixed wing used to be classed as the slow SAR type role that we used to have. Very much more today is that the control response of this aircraft is very similar to a fixed wing, a very instant response. And you can transfer from 90 degrees left to 90 degrees right almost as quickly as you can with a fixed wing aircraft. Its maneuverability as well, because of the combat situation and the weapons that we carried, is again very much more instantaneous response. And I think any fixed-wing pilot would be very surprised if he actually flew a modern-day helicopter to realize just how close we've got now to the jet aircraft, if you like, the fighter, in terms of control response. The flight envelope of any aircraft is that we've obviously got to fully explore before we give it to any of our customers, be it military or civil. So what we do is that we take the aircraft to its limit as far as speed is concerned and C of G's are concerned, and also angles of bank as concerned. So where you see us at shows, for example, doing torque turns, stall turns, they're something that looks good for the crowd, but they are actually used by us to put the aircraft through its full roll capability, if you like. I think always, though, the difference is that every time we fly is that we're up there for a purpose. Now, that may sound silly, but instead of just flying from A to B, we're actually doing a specific task. So time actually in the air goes very quickly, and we compress always a lot into the time that we do fly. So throughout a working day, I may only fly, say, 3 times, and they may be only 5–10 minutes duration, but there's a lot put into that, and a lot of briefing and debriefing that goes on as a result of that, and a lot of report writing that goes on as far as those 5 or 10 minutes work is concerned.
The test pilot's job in the development of the large commercial transports, like the new Boeing 747-400, requires years of work before the first test flight. Ken Higgins, Director of Flight Operations at Boeing.
Well, my particular job on the 747 was more from a stand back and look at not necessarily the details, but the overall program. However, the test pilot who is assigned to the test program works with the design engineers from the very outset of the program. This can be as much as 2 years before the announcement of an active new airplane program. The total time involved before the first flight can be as much as 4 years before the first flight of the airplane. Well, of course, when we design the airplane, the very prime consideration is passenger safety. That's the beginning point. We nor the industry could ever afford. We would not have an industry if passenger safety were not the prime consideration. The main area that passenger comfort enters into my job is in the area of development of the automatic flight control systems. Now, the automatic flight control systems, one of their purposes is, in fact, to make the airplane fly very, very smoothly so that in the back of the airplane, the passenger who's eating dinner, the passenger who is having a drink, can do that in comfort. So we spend a great deal of time working with the automatic pilot to make sure that it operates very, very smoothly so that the passengers in the back of the airplane don't even know that the airplane is maneuvering.
In May 1988, the flight test program moved to Edwards Air Force Base in California to take advantage of the clear skies and the long approach capabilities of the 15,000-foot runway. Here, tests on aerodynamics, propulsion systems, flight controls, automatic pilot, and brakes were performed. This is a digital avionics airplane designed to be flown with a 2-man crew.
Most of the work on the 2-crew cockpit is done in the early design phases. We look at every single possible type of incident, type of malfunction that can go wrong, and design that to be operated by a two of crew very, very early in the design. The flight testing program itself is just a verification that those designs that we did do work correctly.
In one in-flight test, called a wind-up turn, the pilot puts the aircraft into a gradually decreasing turning radius. Information is then fed into the computer, which applies pressure to the pilot's control stick, thus simulating the feel of the maneuver for the pilot. Ground effects testing requires multiple repetitions as the 400 in autopilot control is examined for handling and stability in various approach attitudes. Different flap settings, power levels, and natural elements, such as crosswinds, provide a multitude of factors that the test pilot must make certain will not affect the safe performance of the aircraft. The test program will log 2,300 hours. Of this, the test pilot will spend 1,100 hours in the air with this airplane before it can receive FAA approval for commercial operation. Today's test pilots are exploring the frontiers of flight, advanced performance, stability, and control technologies that will be employed in the civil and military aircraft of tomorrow. The Rafale, a prototype of a dual-role fighter aircraft being developed for the French Air Force and Navy by Dassault Breguet, is now being tested. Jean-Mateau Marad is chief test pilot for the Rafale program.
Yes, for me the main role of the test pilot is to be between the engineers and the users. The users are the French Air Force pilots, and I have to be in between all the time to know on the both sides what is to do. In the modern war, the task of the pilot is always increasing and increasing. And if you want to do that with only one man on board, you have to help it the maximum. And now we are speaking of artificial intelligence, and we are approaching slowly this way, and that's what we try to do on the Rafale. We have no checklist on this aircraft. If you forget something, the system tells you, you forget that, please correct before takeoff. For the first time in our company, we didn't have any correction to make to the aircraft. Everything was almost as predicted, and the aircraft you see today is exactly the same as at the last show. We had 30 flights in '86. We have now 345 flights. 18 pilots have flown the machine, 18, coming from the French Air Force, the French Navy, and we make no correction. The airframe is exactly the same. The only changes we made was in the fly-by-wire software, of course, and it was all the time only to improve the system. From the beginning, the Rafale was designed to be a dual-role aircraft. My deputy test pilot comes from the Navy, Yves Kerhervé, and he makes a lot of carrier approaches and touchdown also on the airfield, and on the deck, on the aircraft carrier, we make also a lot of approaches, more than 300 now.
Unlike the Rafale, which is a prototype aircraft, many of today's test pilots are testing aircraft that are technology demonstrators. These machines include advanced aerodynamic design and experimental control systems that, if proven successful, will be incorporated into the operational aircraft of the future. Steve Ishmael is one of the NASA test pilots flying the X-29.
The role of a test pilot, or any pilot, in a highly augmented system like the X-29, it varies. There's not just one role that you fulfill. the fact that you cannot do everything yourself, that you need a computer, doesn't mean that you obviate the need for a man in the loop. And first of all, test pilots, are frequently, when you engineer a system and when something comes up that you have not anticipated, you frequently present the data to a human being and say, you decide what's going on, like that. It's not necessarily an emergency, but there can still be puzzling aspects that were not foreseen when you were initially designing and building the system. And so you say to the human operator or the pilot, you know, this is what we think is happening, is this reasonable? Well, and so you involve the pilot in, is the airplane behaving in a reasonable fashion? Because it operates in many different environments, not all of which can be anticipated when a control law engineer sits down and starts writing out gains that go into a table that the control law uses, you know, to fly the airplane.
Mine is turning to east.
Northrop's Advanced Tactical Fighter program is testing aerodynamic concepts and performance capabilities to be incorporated into an aircraft that is still on the drawing board. Paul Metz, Chief Test Pilot for Northrop.
We've all been operational pilots. We've all been fighter pilots. I have combat experience, so I have been there. I know what it's like to be crushed by 9Gs and check 6 o'clock. I've experienced the terror of being shot at. So I have the operational experiences. What I also have is the ability to translate those operational experiences into engineering terms. And hopefully, with the assistance of the engineer, we create a product that really fills the fighter pilot's needs. Well, I'll spend 3 simulator sessions a week here working on flying quality. We're also involved in simulations of the complete weapon system, this tactical simulation that we have there behind us. That may be as much as a sortie a day over a period of 6 weeks, 4 hours at a time. So a tremendous amount goes into simulation.
He's dead.
I'm also involved in the systems design. I'll be working with an engineer on the fuel system, the electronic control systems for the flight controls, just the complete gamut of pieces that go into the airplane. The test pilot's role in a simulation such as this one is to act as a translator again. For example, we might be running a tactical simulation in which we have a number of enemy aircraft being attacked, surface-to-air, air-to-air threats that we're trying to avoid. And we might find in the process that the radar needs a certain capability in terms of scan pattern, detection range. Well, today's test pilot is a translator. He interfaces between the operational pilot, who has real requirements based on his training and his experience, and the engineer, who has the skills necessary to create hardware and software. And our task is to bring the understanding to the engineer of what it means to pull 9Gs and turn your head and check 6 o'clock, and allow that engineer to translate that into the equipment that will really satisfy the operational pilot's needs. The operational pilot may not be able to express his requirements in engineering terms, and our task is to make that transition.
To meet the expanding challenges of flight testing the aircraft of tomorrow and to reduce the ever-present risk, rigorous academic and skill training have been instituted in test pilot schools throughout the world. The training curriculum established here in the U.S. Navy Test Pilot School at Patuxent River, Maryland, and in the U.S. Air Force Test Pilot School at Edwards Air Force Base in California represent the standards used internationally for test pilot certification, including the UK's Empire Test Pilot School and the French Test Pilot School. We came to Edwards to learn what it takes to qualify as a test pilot. Colonel Mike Kostelnik.
The test pilot school selection process is extremely rigorous. We look for individuals in basically 3 categories. First of all is academic credentials. We look for the specific courses of engineering study that the candidates have. The most important, of course, for test pilots, realizing that we have both test pilot, test navigator, and test engineer candidates, is the flying for the pilots. We're looking primarily to have the best operational experience we can get from the field, experience in multiple airplanes, be they fighter or multi-engine types. And the last category that we look at very closely is general professional military qualities.
Major Harry Walker, Chief of the Special Projects Division at the Air Force Test Pilot School.
The test pilot school is broken down into three major phases: a performance phase, a flying qualities phase, and a systems phase. Inside the 1 year school, we then teach very detailed academic courses on starting with subsonic aerodynamics, going all the way up through hypersonic aerodynamics. And then when we get into flying qualities, we talk about the military specifications on how piloted vehicles need to be built so that the handling qualities are good or better than they used to be necessarily. And in the systems phase, we dwell on avionics and how the subsystems of an aircraft will then enhance the missionization of the airplane. Those are the three major blocks of instruction.
We study everything in depth before we go and do something. We take out as much risk as we can, both for the people and for the machines, and we're very careful in executing a very restricted mission card.
Student test pilot Captain Ed Wilson is conducting a briefing for a flight that will involve a series of spin tests. His instructor, Major Chuck Stewart, is seated to his left with Captain Bob Demick, a student flight test navigator who will monitor the telemetry station during the test flight. To his right are two instructor pilots who will fly the safety chase plane to observe and inspect the test aircraft during the test flight. Captain Wilson reviews the test card.
The card has a sequence on it for what spins we're going to be doing today. The first one, once in the spin area, we'll be going a phase C stall and be left adverse controls for 3 seconds. Then come back around, we'll do the first spin. It'll be a 1G erect right spin with a NASA standard recovery. And then a 1G roll coupled to the left, and that'll be a flight manual recovery. So you see the airplane roll. You'll see the airplane roll 270 degrees to the right, and then I'll be on the left rudder, and we'll couple up into a spin there.
When the briefing is completed, student and instructor proceed to the flight line and the T-37 training aircraft. After a pre-flight ground check and sign-off, the crew straps in. The test card is secured to the right leg of the student, and the pre-flight checklist is completed. The signal is given to taxi to the runway. The chase plane, a TA-38 Talon two-seat aircraft, follows close behind. In the telemetry station, Captain Demick checks out the instruments that will track and record all phases of the test flight. The planes are picked up by the space positioning tracking cameras.
Clear for takeoff, the wind is calm.
The chase plane has just been cleared for takeoff. This camera will record the entire mission from a ground-based tracking station. The top line of text identifies the aircraft and mission information. The lower line, from left to right, gives the day of the year and the hour, minutes, seconds, and thousandths of a second in Greenwich Mean Time. The telemetry observer checks the test card. The test aircraft takes off and is joined by the chase plane. Together, they fly to the test range. Over the range, the T-37 pulls away to prepare for the first test on the test card. The T-38 chase plane must stand off at a safe viewing distance during each of the test maneuvers. The tracking camera, however, clearly records each test. This mission included 3 stall tests and 7 different spin tests. The third spin test on the mission card was a 0G inverted spin to the left with a planned NASA-modified recovery. You hear the student pilot, Captain Wilson, recording data during the spin.
Okay, ground, we're in a spin. There's 1 turn, 24.5. 2 turns, 24. ALA's bouncing all over. 3 turns, we got 23.5. Being NASA modified recovery, 30 knot, 130 knot. Recover, let's spin. Don't want to do that. And we're recovered.
No, don't do that.
Don't do that.
Don't touch the red engine.
Okay.
You heard the instructor pilot, Major Stewart, with a word of caution during recovery.
Okay, now you got the engine.
Okay. Now we're off left. I would dive at 15. Ignition's off.
Good call, TM.
After each test, the student reviews the data he has taken. And for this one, he was complimented with a good job by the instructor.
Wrapped up into a fairly oscillatory spin. We were inverted. I had probably plus or minus 20 degrees on the oscillations there.
Captain Demick, the telemetry observer for this mission, also records the performance data on his copy of the test card to be used in the debrief and post-mission analysis. After each spin test, the chase plane moves in close and completes a visual inspection of the test aircraft to ensure that the violent forces acting on the plane during the test have not caused any structural damage. The entire test mission ran approximately 55 minutes. The final data is collected at the telemetry station. After completing the mission, the aircraft returned to base. The student test pilot, the instructor pilot, and the crew of the chase plane will join the telemetry observer for the debrief. We asked Captain Wilson to describe the roll-coupled inverted spin that we recorded.
In the roll-coupled inverted spin, it's pretty violent in the airplane. First of all, we're strapped in as tight as we can because we'll be tossed up against the canopy of the aircraft if we're not. So in fact, it feels like a cartwheel almost as you enter the spin. You start a roll and then stand on a rudder and push the stick forward, and the airplane kind of tumbles across like this. And it feels like that in the airplane. You're slung out of your seat at about, you go to about 1.5 to maybe 2 negative Gs initially, oscillating back and forth for the first few turns around where you're not really in a spin but in a gyration. We call it post-stall gyration. And then you settle into just a spin where all you see is ground below you, and you're stable at roughly one negative G, hanging in the straps, trying to hold the stick at a certain spot where you're floating up and trying to push the stick over as far away from you as you can to hold the spin in. And then when you come to recover, it's just a nice feeling to get out of that kind of spin because it's an uncomfortable spin for you.
Captain Demick, the telemetry observer.
I thought the test went very well. Monitoring it from the telemetry room, we're able to see what the airplane's doing in a no-threat type environment. The things we were looking for were crispness of inputs, correct recovery, what actually caused the aircraft to recover, and I think we got some valuable data out of the mission. The inputs were all proper in the right sense. The pilot's comments were very good, and when we get the final analysis done, overall the data should help us a lot.
Well, I think the Air Force Test Pilot School is a very unique community. I didn't know too much about it as a young man. Of course, I grew up watching the space program and always had an interest in that, and ultimately kind of evolved here because I had the technical background and got interested. It is, I think, something for the younger viewers. It is a goal that is certainly achievable. People tend to think about the test pilots as perhaps prima donnas or something special. The ones I see around here, and I think in the show here you'll see and have exposure to others, I think we're just real people. We're very cautious, we're very concerned, and we're very professional, and we're very much not different from the other military or aviators that you find.
The caution, concern, and the professionalism of the test pilot is expressed in every facet of his work. Today's test pilot is intimately familiar with his machine. His technical knowledge, together with his consummate flying skills, gives him the ability to objectively communicate the specific performance characteristics of the aircraft to the engineers and the designers on the ground and in the laboratories. This work requires that he measure the danger and accept the personal risks that are inherent in advancing the science of flight. This is the task. This is the role of the test pilot.
The days of Clark Gable and the white scarf and the blood coming out of his ears and that kind of thing, they've been gone long before I ever got in the trade.
My life, of course, is attached very closely to the well-being of the airplane.
I've got to rely on my engineers that they put it right before I go off and test it. Otherwise, we wouldn't be doing it.
And having a pilot in the loop adds qualitative observations.
We aren't daredevils. We have a job to do, and we go out and develop the technology to do the job.
The risk in test flying is one that we all face. It's one that we all accept.
Still very much in control of the airplane. The computer provides an interface between the flying qualities of the airplane and the human being. And that's as simple as it gets.
I'm just a human being. I'm not an aviation pope. I'm a flying sinner.
For test pilots, the most interesting thing is to discover a new aircraft.
Well, the role of the test pilot is also to determine where this borderline is between what the airplane can do and what the human being can tolerate.
And I enjoy being part of that team. I consider myself extremely lucky to be the last man in the last seat, if you see what I mean.
Well, my view is that if you don't make a manned vehicle and a man ride in it, to hell with it. What use is it to the human experience?